In this lecture, we will quantify potential energy, and we will also then move towards a statement of conservation of energy. This lecture begins immediately after the last lecture left off. What I need you to do is I need you to copy down this information, which I still have on the board from the previous lecture. In the previous lecture, one half of the calculation that we did was we calculated the work done by gravity in lifting an object through a displacement, a vertical displacement, h. We also saw that the path itself doesn't matter. So if I take an object and I lift it vertically like so, the work done by gravity, as we saw, is negative mgh. This is one half of the calculation I performed in the last lecture. Therefore, the minimum energy that I use to overcome the force of gravity, the work done against gravity, is positive mgh. Here's how we write that. Once again, you have to be very specific here with your phrasing. The work done against gravity in lifting the object from point A to point B through a height change h, by definition, is the negative of the work done by gravity. So showing all the negative signs, this is the negative of negative mgh. This is equal to positive mgh. This positive mgh is now interpreted as the change in the object's potential energy as we go from point A to point B. We use the variable capital U to describe potential energy, like so. Now, technically speaking, what we've calculated here, the work done against gravity, is interpreted as a change in gravitational potential energy as we go from point A to point B on the diagram. Okay, now let me further illustrate here on the lower board. The change in a quantity is always the final value minus the initial value. The initial value is 0, however, at point A on the diagram above, because that's what we're treating as the origin. We're thinking of that as 0 height. So this right here is 0 at the origin. That is position A on the diagram. So then therefore the final potential energy at point B on the diagram above is equal to mgh. This completes here the mathematical steps of what I originally outlined just qualitatively at the beginning of this process a couple of videos ago. Once again, qualitatively, I described it to you initially in the following way. You lift an object vertically, the work done by gravity is negative mgh, therefore the work that you do against gravity is positive mgh, that then becomes the potential energy of the object. That's this calculation here. Okay, and then the next step is to come up with a statement of conservation of energy. We will once again use the pendulum to illustrate. I will show you that demonstration once again in just a few minutes. But let me now go ahead and do some erasing here. Okay, now we do in fact come up with a statement of conservation of energy. And we will specifically use a pendulum to illustrate. Okay, now whenever you're describing energy transfer, or in this case, energy transformation, your starting point is always the same thing, and it's the work energy theorem. So what we're going to do is apply net work equals change in kinetic energy between any 2 points in the oscillation. Okay, now recall my description of the pendulum. We're ignoring friction between the rope and the attachment. We're ignoring air resistance, and the tension does no work. Therefore, the only thing that's important is gravity. So if I apply the work energy theorem between any 2 points in the oscillation or the pendulum, the left-hand side of the expression is only one thing. It's the work done by gravity. Like so. Okay, now, from just a few moments ago, the work done by gravity is the opposite of the work against gravity. Notice the negative sign. However, also from a few minutes ago, the work done against gravity is the change in gravitational potential energy between any 2 points in the oscillation. Like so. And now take this term here and move it to the other side such that we obtain the following. Let me write it like this. Like so. This is a statement of conservation of energy. Here's what this statement is saying. Once again, this is between any 2 points in the oscillation. Between any 2 points in the oscillation, if we add together the change in the kinetic energy between those 2 points and the change in potential energy between those 2 points, we always end up with 0. The left-hand side of the expression here is interpreted as the change in the total energy E of the object. If the change in the total energy E of the object is equal to 0 between any 2 points in the swing, this then means that the energy E is a conserved quantity. It is a constant. Another way of exactly saying the same thing is as follows. For a single point in the oscillation, the energy E, which is a combination of kinetic and potential energy, is always equal to the same number. It's equal to a constant. Both of these expressions are mathematically saying the same thing. It's saying that the energy is conserved. This is between any 2 points in the swing. This is for a single point in the swing, a single point in the oscillation. Let me illustrate actually now physically with the pendulum. Okay, I'm going to have to retilt my camera here. Like so. Let me tilt the camera down too. There we go. Okay, now let me go ahead and perform the demonstration here with the pendulum. Right now the pendulum is at rest and it's at its equilibrium position. So let's consider this right here to be height 0. So then therefore right now there's no potential energy and there's no kinetic energy. And then I come along and I do this. I lift the object through a vertical displacement like so. I undergo right here a height change h. So I do work against gravity in lifting the pendulum to that height. The amount of work that I do against gravity is equal to the potential energy, mgh. However, the pendulum right here is not moving. It has 0 kinetic energy. So right here, its total energy E is all just potential energy, mgh. But then as I release it, because the energy is conserved, all of this mgh of potential energy right here transforms into the exact same amount of 1/2 mv squared kinetic energy at the bottom of the swing. And then on the other side of the equilibrium position, the process just happens in reverse. All of the kinetic energy of 1/2 mv squared here turns into the exact same amount of mgh on the other side. The total amount of energy, the combination of kinetic plus potential at any single point in the oscillation, is always the same value. So then therefore, I now understand why this pendulum, for example, when I release it from rest like so, right up against my chin, always returns to its original height. It always returns to its original height because the energy is conserved. Where have we seen this before in class, where an object was released from rest at some height, and then the object always returned to its original height? Galileo's experiment that he used to discover inertia. Remember that he never did understand why the object always wanted to seem to return to its original height, but he did use his experimental result to ultimately discover the law of inertia. We now know why that is, and it's because the energy of the object is a conserved quantity. So I demonstrated this at the time with the pendulum. Now we understand why the pendulum always returns to its original height. The reason for that is because the energy is conserved. Now, if you watch the pendulum oscillate here through a couple of oscillations, you're going to begin to notice that the height of the pendulum does in fact begin to decrease. The reason for that, of course, is because there's a little bit of friction here between the rope and the attachment, and there's also a little bit of air resistance. These types of forces are called non-conservative forces, and in this particular case, they then take energy away from the object and they transform it into heat. The only way in which the object could rise to a height that is greater than its original height is if somewhere in the swing, something else does work upon it. Say, for example, like so. and then I do something like that. In doing so, I add energy to the object. But if I don't push on the object after I release it, and if we ignore friction between the rope and the attachment, and we ignore air resistance, then this pendulum will literally oscillate forever, always returning to its original height. Okay, let me tilt the camera back. Like so. And now it took the last couple of lectures here that you have observed in class today, it took the last couple of lectures, as you saw, to arrive at this expression of conservation of energy. This, yes, admittedly, these lectures, of course, qualitatively are a bit difficult in understanding exactly what the calculations mean that I performed. If necessary, please review them. However, using this expression, as you'll see subsequently in example problems, is actually quite easy. And the reason for that is because we don't have to bother doing any more dot products. We already know, for example, that when it comes to a height change, the punchline is changes in kinetic energy plus changes in potential energy is equal to 0. So then therefore, mathematically, all that we have to do is fill in the terms into this expression to calculate whatever it is that we're looking for. At this point, we are moving beyond the work energy theorem. We don't have to bother doing any more work calculations when the energy is conserved.